So today it's my pleasure to introduce Sabina Manz, who recently defended her master's thesis about a month ago, or less than a month ago. So it's a bit of background on Sabina. She did her undergraduate degree in sports medical engineering at the University of Applied Sciences, Koblenz. But she did her undergraduate thesis here at the University of Calgary, working with Dr. Ben O'Nig and Amy Smith, or Amy Mears now, on vibration transmission to the lower limbs with varying blade holder stiffness. Based on her interest from the undergraduate thesis, she pursued her master's degree here at the University of Calgary with Dr. Ben O'Nig, and she will talk about some of that research here today. So Sabina's research interests in general are on smart technologies and with applications to sports, fitness, and biomechanics. And in Sabina's words, her biggest scientific accomplishment to date was getting a master's degree with a specialization in biomechanics without using a motion capture system. And then when asked about her future plans after her master's, Sabina said she will try out as many things as possible with many different industries to find out what she likes best. Or in short, she's not going to stay in academia. So one interesting fact about Sabina is that she loves to puzzle and has finished the world's most difficult jigsaw puzzle, as you can see on the screen here. So it consists of 529 pieces showing penguins and nothing but penguins. And it's printed on both sides. The top and the bottom pictures are identical, but rotated 90 degrees with respect to each other. Now I said I wouldn't, to myself, that I wouldn't make the same joke twice, but today we also matched the coffee to the speaker. And just one sec here. All right. So it was a perfect fit. Based on her description of loving puzzles, today's coffee is smartass. And if you look at the caricature on the front, it has a donkey with glasses that might look a bit like Sabina.
Glasses.
Just the glasses, just the glasses. All right, so let's have Sabina discuss and potentially solve the puzzle of, sorry, it was too bad. How comfort could influence your footwear preference. The floor is yours, Sabina.
Running is a very popular form of physical activity or sport. In the United States alone, over 47 million people participate in running. Those runners purchase footwear that's worth almost $16 billion every single year. There's a wide selection of running shoes that those runners can choose from, with the first running shoe, as I showed here on the slide, that came out in the year 1832. So since then, there has been a lot of research done on running shoes that led the development into different directions. However, it's interesting that systematic running shoe research hasn't started until the 1970s. The running shoes that are currently on the market range from minimalist shoes to highly cushioned shoes and many other models as well. The literature suggests that there are three main reasons why this development has been driven into different directions. The first reason is a decrease in injury risk. So researchers have tried to eliminate footwear that was associated with a higher risk of injuries. Second, performance. Since the running shoe is the only tool that a runner can choose from, it makes sense to look into the effect that a running shoe would have on performance. While injury risk and performance have received the majority of attention in the literature, it is also interesting to see why comfort did not. More specifically, comfort is one of the most important footwear features, of a running shoe, and can be different for every single individual. That means comfort is a very subjective measure. When looking at a bigger population, we can find groups of people that have similar preferences and would therefore form functional groups. In that context, a functional group would mean that if we were to give them a certain footwear intervention, they would react in a similar way. So the reason why the focus of the literature has been on injury prevention and an increase in performance and not comfort is mainly because to date, comfort is still not well understood or easy to quantify. The way out has been to try and relate comfort to shoe properties as well as biomechanical measures such as ground reaction forces or plantar pressure. And there's quite a substantial amount of literature out there. However, I'm going to focus on 3 studies today where one group of researchers have tried to relate comfort with the amount of cushioning in a shoe and the ground reaction forces during running. So what they found was that if a shoe was perceived as less comfortable, that was associated with less amount of cushioning and a higher loading rate peak. A very similar study, however, did not find any relationship between comfort and biomechanics, which is very contradicting to the results in the first study on this slide. What is known, however, is that when we change certain properties about a shoe, that will change the running biomechanics, such as the third study on the slide shows, where an increase in cushioning and heel height leads to an increase in heel strike angle and plantar flexion velocity. So again, there's a lot more information out there. The problem with that is that it is not coherent or conclusive. That means the relationship between comfort, biomechanics, and shoe properties is still unclear. If we want to take this a step further and we want to use that knowledge in a shoe store, where we want to give recommendations to runners as to which running shoe would be best for them, we can't really use what's known so far because everything was bound to a laboratory environment with very expensive equipment. So what we suggested was the use of newer technologies such as inertial measurement units that allow us to collect data in almost every environment. And therefore, the purpose of my master's project was to distinguish movement patterns while running in a comfortable and an uncomfortable shoe condition. We further wanted to see if these differences in the running kinematics were localized to a specific body segment. And then lastly, we wanted to see if the classification tool, if it's a linear or spherical classification, would make a difference. To do this, we tested 9 different shoes that systematically differed in 2 properties. The one property was the midsole density, and the other property was the heel drop. By changing those 2 shoe properties systematically on 3 levels, we get to this 3x3 matrix as shown in the slide here. And I've done some mechanical testing with the shoes that resulted in the values that you can see here on the slide. However, in general, when we go from the left side to the right side of the matrix, while staying within one row, we have a steady increase in midsole density from soft to medium to hard. And similarly, when we go from top to bottom while staying within one column, we have a steady increase in heel drop from low to medium to high, while the midsole density stays constant. So we gave these 9 shoes to our 80 participants in the study, and we asked them to fill out subjective questionnaires focusing on their perception of comfort of the shoes. We also asked them to rank the shoes so that we could determine everyone's most and least preferred shoe condition, because then we asked them to perform overground running in those 2 shoes. While our participants were running, they wore 5 inertial measurement units that measured accelerations and angular velocities at 5 locations of the right side of their body, being the dorsum, the heel, the gastrocnemius, the wrist, and the ACES. So in order to answer the first question, whether there are differences in the running kinematics while running in a comfortable and an uncomfortable shoe condition, we first wanted to see which shoe conditions our participants ran in. So these 2 matrices again represent the 9 shoe conditions that we tested in the study, and each number in one of the boxes represents the number of runners that ranked a certain shoe as their most preferred on the left and as their least preferred on the right. So if we add up the numbers from one matrix, we end up having a total of 80 trials. 17 out of those 80 trials were run in the bottom left shoe because 17 out of the 80 participants said that the bottom left shoe was their most preferred. On the other side, for the least preferred condition, 12 participants ran in this exact same shoe because they said that was their least preferred shoe condition. So at this point, it's important to say that we're making comparisons across different shoe conditions because, as I mentioned, comfort is different for every individual, and therefore the most and least preferred shoe conditions were also different for our 80 participants in the study. So we have 80 trials, 2 conditions, which leads to a total of 160 trials that were all time normalized to 100 points. And then we used the 30 variables that we obtained from our 5 IMUs in order to reduce the dimensionality of our system by using it as an input for a principal component analysis. By doing that, we could determine the dominant parts of the movement pattern while running in our shoe conditions, which were then used for classification using a support vector machine and spherical classification. So for each of our tools, we calculated a total of 160 classifications. And the reason for that was because we wanted to see how much information do we need in order to get to our highest classification rate. So for the first classification, we only used information from principal component 1. We calculated the classification rate. We added principal component number 2, calculated the classification rate again, and so on until we used all the information that we got from our PCA. Here's an example of how this looks like for the first 3 principal component vectors. So you see the first 3 principal component vectors on the axes here, and a total of 160 trials that are shown in pattern space. In red, you see the trials that were run in the most preferred shoe condition, and in blue, you see the trials that were run in the least preferred shoe condition. So for each participant, we have 2 dots in this graph, one in red and one in blue. So when we look at this, our goal was to distinguish the movement pattern between running in a comfortable and an uncomfortable shoe condition. But when we look at this, we don't really see a separation, which was what we were hoping for. This becomes quite clear when we look at the variance that each of these principal components explains. Usually when we do a PCA, we expect that the dominant parts are in PC 1, 2, 3, or the lower numbers, but when looking at the number or the amount of variance that is explained by those lower number PCs, we can already tell that that's not a huge amount. And that's exactly what this graph shows as well. We have the number of principal component vectors on the x-axis. That means the amount of information that we use in order to classify our trials. And then we have the classification rate on the y-axis. So usually what would happen is with the first few principal component vectors, we can explain a lot of the variance in our system and would therefore get a higher classification rate. In this case, however, if we look at the first few principal components, we don't really get a high classification rate, which is a problem. In fact, to max out our classification rate using a support vector machine, we needed a total of 123 principal component vectors. The maximum that we could found was 31%, which is not very high. And there are 3 possible reasons as to why this might have been the case. The first reason is the movement patterns might have been too similar. So if you remember back to the data in pattern space, we didn't see that real separation that we were hoping for, and that might have been due to the fact that the shoes were very similar. We couldn't really change that fact because they were produced in such a manner that they would fall within the allowance that the footwear company would bring them on the market. The second reason why we might have not seen a difference was because the comfort or the perception of comfort may have not been different enough. We have to state here that none of the shoes was specifically designed to cause discomfort. However, we asked every participant to rate the shoe on a scale from 1 to 10, and then also rank their most preferred and least preferred shoe. So let's say one participant rated all 9 shoes a 7 out of a 10. We then still force them to tell us which one of those 9 shoes was your least preferred and which one was your most preferred. So the actual difference in the perception of comfort may have not been big. And then lastly, it is possible that the support vector machine may have just been the wrong approach or the wrong methodology in order to determine those differences in the running kinematics. So because we were only able to get low classification rates, we were also interested whether with the whole data set we're just trying to fit noise, and maybe if we're focusing on a single body segment, we might be more successful. So that's what we did, and again, we had 5 different locations on the body that we put IMUs on. We had 1 on the ACEs, 1 on the wrist, 2 on the shoes, and then 1 on the gastrocnemius. To limit the number of variables, we calculated resultant accelerations and angular velocities for all 5 sensors, and therefore we ended up with a total of 10 variables that we could choose from. By choosing between 1 and 10 of those variables and use all possible combinations, we ended up with a total number of 1,023 combinations. So one of those combinations, for example, was only using the resultant acceleration measured at the dorsum. Another combination may have been the acceleration of the dorsum and the angular velocity at the hip. For each of those 1,023 combinations, we then again calculated classification rates for 1 to 160 principal component vectors, and therefore we end up with a total number of classifications of over 160,000. So the distribution of our success rates of those 160,000 classifications is shown in this graph here. You have the classification rate from 0 to just over 50% on the x-axis, and the number of combinations that fall into each of those bins on the y-axis. And what we see here is that the majority of classifications fall within the range of 10 to 40% correctly classified trials, which is very low. Our maximum actually is just over 50%. The reason why we can't see it here is because the y-axis is in thousands, and only one of the combinations that we tested was actually resulting in 53.1% correctly classified trials. And that specific combination of variables was only using the resultant acceleration at the heel. So what we learned by only using a subset of the data was that we could slightly improve our classification rate. However, it was still relatively low with only 53% correct. What was interesting to us was to see that it seemed like the heel sensor carried the most relevant information. Lastly, I just wanted to compare 2 different classification tools, and the one that we're comparing the support vector machine against is spherical classification. A lot of people ask me, why did you use spherical classification? And there's a simple reason to that. So let's assume our data is organized in a manner such as on the slide here, where we have 2 different groups of data, one represented by the blue circles and the other one represented by the red triangles. What the linear support vector machine does, it basically just tries to find a hyperplane that best separates those 2 groups. In this case, because we have a 2-dimensional data set, that hyperplane would just be a straight line. And I think we can all agree that if we're trying to find a straight line that best separates those 2 data sets, a support vector machine would fail because there will always be data from one group that is being classified into the wrong group. So our approach was to use spherical classification and just see whether we could improve our classification results. So the following few slides are always going to compare the linear support vector machine result on the left with the spherical classification on the right. So the left graph you've seen before. Again, we have the number of principal component vectors on the x-axis, so the amount of information that we used in order to classify, and the classification rate on the y-axis. We've shown that we need a total of 123 principal components in order to classify 31% of our trials correctly. When we compare this to the spherical classification, we only needed a total of 11 principal component vectors to get to a maximum of 54% correctly classified trials. So it seems like we get better classification rates with the spherical classification. However, somewhere around 50%, and we still don't know if that is actually better than chance or not. So what we did was we used a binomial test in order to simulate how many trials we would have to correctly classify in order to be significantly better than chance. So we set our level of chance at 50% classification success, because we have the same amount of trials that were run in the least preferred condition compared to the most preferred condition. And with a significance level of 0.05, we could then set two thresholds. One threshold was 43.8%, below which we would say the classification rate was significantly worse than chance. And the second threshold at 56.3%, above which the classification rate would be significantly better. So for the next slide, I've color-coded the areas of the classifications that fall into either significantly worse than chance in red or significantly better than chance in green. Again, we have the linear support vector machine on the left and the spherical classification on the right. And we see the distribution of those 160,000 combinations where we calculate the classification success for. So for the linear support vector machine, we have a range between 0 to 50% correctly classified trials. And I've shown this graph before where the majority of classifications fall within 10 to 40%. And actually over 99% of those combinations resulted in a classification that was significantly worse than chance, so below that 43.8% threshold. When we look on the other side at the spherical classification, we get a distribution that reminds us much more of a normal distribution, where we have classification success rates between 40 and 60, with a small amount that is significantly worse than chance, and a slightly bigger amount that is significantly better than chance. So when we put these numbers next to each other, we could see that we could improve our maximum classification rate from the support vector machine from 53 to almost 62%. And from 0% of the combinations that were better than chance, we could improve that to 8% of the combinations that were actually significantly better than chance. So we can say that the spherical classification slightly outperformed the support vector machine. However, it wasn't to a substantial amount. If we take, for example, the 60% that we can correctly classify and use this approach in a shoe store, and let's say we have 10 people coming to the store, we would still have 4 that leave with their least preferred condition instead of their most preferred condition. So again, our goal was to find those differences in the running movement pattern that could classify a trial that was run in a comfortable shoe condition from a trial that was run in an uncomfortable shoe condition. And we were quite unsuccessful based on our maximum classification rate of just over 60%. As I mentioned earlier, that might have been due to the fact that the movement patterns were quite similar. And that is in agreement with the preferred movement path paradigm that states that the proportion of runners that actually change their movement pattern is dependent on the magnitude of the change between the shoe conditions. So if we have small differences between the shoes, as it was the case in our study, we wouldn't find a lot of people that actually adapt to a change in footwear condition. And then, of course, we could also argue that the perception of comfort between the two shoes wasn't big enough. For future directions, we could still look into other biomechanical or neurophysiological variables, such as amplitude and frequency content of muscle activity as well as soft tissue vibrations. However, we think that that is most likely not the case. The reason for that is I also collected over 80 functional variables that I did not present in this talk today. And those functional variables were such as grip strength, balance, foot sensitivity, anthropometrics, and so on. And we could not find a conclusive predictor of comfort amongst those 80 variables. So we can say we were quite unsuccessful with this study, and we can't really say what is the reason why a certain individual will perceive a shoe as comfortable or uncomfortable. So if we circle back to our initial goal, where we want to give recommendations in a shoe store as to which shoe is best for a certain individual, we can say that we're just not quite there yet. So with that, I would like to thank you for your attention, and I'm happy to take any questions.
All right, any questions for Sabina? John first. Thank you.
When you show your initial matrix, like if you could go back to that slide, the 9 conditions, and then how many people preferred what shoe? Yeah, no, you've got another one where you talk 17 people. Yeah. So when you see that, I look up at that and I see kind of clustering in the corners of both of them. Could that be related to the shoe design? Like is that matrix developed around this shoe is the most this, and this shoe is the most this, the bottom right-hand corner is this, the top left-hand corner is...
Yeah, so if I go back to the other slide.
Yeah.
If you look at the left-hand side, those are all shoes with a soft midsole density. Yeah. So they have that one feature in common, and then they just vary between different heel drops. So one could say that all the people that fall into that left part of the matrix like a soft shoe, yeah, and they just don't care about the heel drop at all.
Yeah. So is it possible then to classify that data so that it polarizes to that one top corner and down, and where people fit in relationship to that?
Yeah, so we actually did some grouping with the data too. So we were trying to look at, are we more successful if people like soft shoes, and then compared to if people like, for example, low shoes. So we put people in different groups, yeah, and then we were trying to compare the classification success of those groups. And then as a fifth group, so we had 4 groups, yeah, the soft, the low, the hard, and the high. And as a fifth group, we actually had people that changed their mind or didn't have like a clear preference. And amongst all those 5 groups, the classification rate did not change. So it didn't even matter what kind of shoe they liked or if they were reliable in assessing their footwear preference. The classification was equally bad.
Was there any associate, or did you look at any kinetomic differences between people? Like really big people preferred a hard shoe, whereas really small, light people preferred a soft shoe?
Yeah. So that was one of the 80 functional variables that I was talking about. We assessed all kinds of anthropometrics from the whole body, like height and weight, as well as a foot scan. So we had all the variables. Yeah.
Yeah, my question's quite a bit related, John, but subtly different. Did you try and classify people who had a strong preference for one over another, rather than they were consistent in saying this one's a little bit more comfortable than that one, or this one's a lot more comfortable than that one? Do you look at that?
Yeah, so what we didn't look at their rating as much. So as I said, they all rated the shoes from 1 to 10. The way we grouped them was we looked at the rankings. So we asked them, out of the 9 shoes, please rank your 3 most preferred, so 1, 2, 3, and then your 3 least preferred shoes, 7, 8, 9. And they actually fill out the questionnaire twice. And then we looked across those 2 assessments, are they consistent with their rankings for their most preferred shoes always being on the left side, and then for that reason they would be classified into the soft group, for example.
Okay, so you don't have any idea how many people would have a strong preference for one over the other to say if that actually could be done or not?
Yes, I could look into that. The problem is that if I do that, I'll probably get or eliminate a lot of people.
Yeah.
So in some of the groups, for example, low and high, out of the 80 people, there was only 10 in there, because almost 40% of those 80 people that we tested here actually fall into that other group that don't have a strong preference for any of the footwear features. So it's hard to further down the numbers and still do those classifications.
Okay. So related to the term comfort, did you define that for the individuals in any way? Or did you just use the word comfort and ask them to define it themselves in their head?
Yeah, so we did not specifically define comfort. What we did do on that 10-point scale, our anchor points were least comfortable shoe I've ever worn and most comfortable shoe I've ever worn.
And during that assessment of comfort, how long did they have to assess each of the shoe conditions?
They could take as much time as they wanted to. I told them that they should think of an in-store assessment. So they'd go into a shoe store and they have 9 shoes in front of them, and then they can just try them all on. They can mix and match, they can walk around, whatever they could do in a store, and then fill out the questionnaires.
They go for a run if they wanted to?
They could like run for 5 meters there and back. I don't know, Brent didn't even have a word for that, in my defense. There's like, it's hard to explain, but no, I'm not gonna. Like I told them they could do like sprint starts or whatever is possible in a shoe store. Like don't go for a 5K run and come back half an hour later. That was not allowed.
Yeah, Lauren.
I think I might have missed it. How long did they run that you were recording data for?
So they ran in both conditions for a total of 4 trials, and each trial was 40 meters long.
Do you think that having them run like a longer distance or something would have made a difference?
Yeah, I think that's a good point. I think the longer you run in a shoe, your opinion on it is going to change. And I even heard from my participants a lot that after they've ran in a shoe for even that short amount of time, they said, oh, I don't even like that shoe anymore. But because we had the intention to apply this to an in-store environment, we wanted to make it as close to that as possible. So we didn't want to let them run for 10 minutes in every shoe, because that's not something they would do in a shoe store with 5 different shoes.
I think that makes sense for like choosing the comfort, but in terms of analyzing the biomechanics, maybe having them run a longer distance.
Yeah.
So the way you assess comfort, it's sort of exactly what people do in a running store. So I understand why you chose to do that. But I feel like when you first put on a shoe, you have this sort of heightened sensitivity to what the changes are, and then maybe if you actually went and you ran in it for a while, like Lauren was saying, like maybe you don't even have to run far. Maybe it's just running around the track once. Maybe all that's gone. Like you don't even notice these subtle differences in midsole density and heel drop. So do you think that if you would have assessed comfort maybe after they were allowed to run in the shoe, that you would be able to see differences?
Well, they did assess before and after. So they assessed before running in them. They chose their most preferred and least preferred. They ran in those 2 shoe conditions, and then they gave them all 9 shoes again, and they assessed all 9 again.
Okay, I missed it. What was the sort of correspondence between first comfort assessment and the one after the run?
What do you mean by correspondence?
Like if I ranked one shoe as the most comfortable, am I very likely to rank that as the most comfortable after I run in it?
For the majority of participants, that was not the case, but that's why I included the ranking from 1, 2, 3, and 7, 8, 9. So within those three, there was a big overlap. But then again, about 30 to 40% of the people were just not reliable at all, or changed their preference so much after running in the shoes that I couldn't assign them to any of the 4 groups.
I'm just curious, on that slide, there's a plus or minus. Is that from different shoes or the result from multiple tests of the same shoe?
That is the standard deviation, because I tested every single shoe, left and right. Those are the values for the right shoe because that's where I had the IMUs. But for example, 122.5 newtons per millimeter is the average of the 3 shoes that are within 1 midsole density, but differ in their heel drop. And just because, so the heel drop was same toe height, and then they just adjusted the heel height. And just by adjusting the heel height, which is where I determined the stiffness of the shoe, you get values that differ between 110 130 newtons per millimeter.
Newly minted best staff member.
So if you looked back at your data since you did the survey at the end, people changed their opinion and what was the most comfortable. If you just looked at their final evaluations, do you think it would change the groupings at all? Or have an effect?
It would probably change the groupings for some of them. As I said, 40%. We could then group those 40% of people that were not reliable when looking at both. The question is that a representative grouping method if they change their preferences all the time or every time you assess it?
That might be something interesting to
Yeah.
look into because like the shoe store model, walking in, putting it on, I don't think really ever gives you a great comfort factor. It's
Yeah.
not until you've actually used the
Yeah.
shoe and done something.
I agree.
All right.
Okay, if we want to continue this study, so you want to look at the different muscles, right? So EMG and the vibration of the muscles. So which muscle would you think that this can be more related?
I'd say for sure lower extremity muscles. And then just because the heel sensor showed us that is carrying the most relevant information, I would say maybe muscles that are active post just before heel strike and just after heel strike.
Read that, sorry.
So I work more with people with very severe gait impairments, and we see a lot of effects with fatigue when it comes to different biomechanical parameters. So did you try looking to see, I know you only ran 40 meters, but in that 4th trial, was there a difference between the 2 shoe types?
No, there was no difference. And I also, I tried to account for fatigue. They, because it was overground running, they always ran 40 meters straight, and then on the way back, they could just walk back. So by the time they were back at the start, they were basically as good as new again.
Questions, Sabina. So you said that this study was unsuccessful. But you had that interesting result with the linear support vector machine showing worse than chance. So given that maybe the shoe store, they may not care about what variables work, but if you just give them the opposite choice of what your algorithm says, isn't that almost a positive result? You just have to say algorithm's wrong and give them the opposite. Do you think that might be something positive?
Yeah, so that's the way I thought too.
Yeah.
If we have 0% correctly classified trials, if we just invert it, we have 100%.
Yeah.
But I actually talked to Vincent about it, and he said that for some reason the support vector machine chooses that this is the best way to separate the data, and we don't know why, and therefore we can't just say we invert it and get high classifications. So we don't know why this happens, but.
Okay. Yeah, Brent.
I think there's a lot of people that would be interested in a comparison between the biomechanics that you get with the IMUs when people, all people run in soft/high condition versus the hard/low condition. So have you ever thought about doing some, I don't know,
I
hypothesis testing and actually looking to see if there are biomechanical differences between these two shoe conditions. You have the biggest population looking at these two different conditions that anybody ever has, I'm sure.
Yeah, so I have thought about it. The problem is that if your most preferred shoe is soft high, your least preferred is not necessarily hard low. So I don't really have that comparison for all participants.
Yeah, but separate, like comfort aside, just on a population level, does running in a soft/high drop shoe change your biomechanics relative to a hard? Because maybe there's no differences in biomechanics between any of these 9 conditions. And the take home is go into the running store, pick whatever the hell you want, because you're gonna run the same no matter what.
Yeah, it is possible. I mean, there has been some research that showed that certain properties of a shoe do have an effect on running kinematics, but for most of those studies, the ranges between the shoes were a lot bigger than.
And they
what
probably
we used
limited
here.
to n equals 10.
Yeah.
Not 140 or whatever.
126.
Yeah.
Has anyone ever tried to define a comfort space where you have not just 3 conditions, but go from like ludicrous levels of heel drop down to 0 heel drop, and just plotted how that space looks for different people, and then look at a bunch of different conditions and just see what it takes to make a shoe comfortable versus uncomfortable, and if there are different functional groups in that area.
I don't know if anybody has done that. I'm not aware of anything. I think the problem here is that shoe manufacturers are probably not interested in those extreme, let's say, heel drop values, because they're not going to bring anything like that on the market. And then again, you are going to have, if you test 100 people with your extreme conditions, you're going to have a proportion of your runners that likes the 0 millimeters heel drop, and you're going to have another proportion of runners that likes closer to a high heel drop. So you're always going to have that spread where different people like different things. So I don't think you're going to get an answer to that question. What is the ideal heel drop, or what is a comfortable heel drop?
Maybe you can have it even the opposite way, where there's a toe rise, and just see where people fall in this. Then you might be able to get a better idea of where people are. It's just an interesting idea just to define the space of comfort.
Yeah.
John?
Kind of carrying on from that, it's like I've always heard it said that choice is the thief of happiness. Do you think you would have seen better results if instead of having 9 conditions, you just had 4? And then, like from a shoe store model, if you just had 4 and it could help separate things, then you could say to people, okay, this cluster of shoes is what you would look for, or this cluster of shoes. Maybe not this specific one, but.
Yeah, so before we started the study, we were actually interested in how many shoes is a human able to reliably assess. And we started off with 4, which were the extreme conditions. And we get the same results with 4 or 9, where this proportion of 30 to 40% of the people is just not reliable.
I'm just curious to know if, because this range of stiffnesses and heel drops isn't like that diverse, did people, first of all, did they know what the differences were in the shoes?
No.
And do you think they could even tell the difference between like the softest shoe and the hardest shoe, really?
Some people did.
Yeah.
Some people were pretty good at telling that one of the properties that we changed was the stiffness of the shoes. I had this one subject that I think was very funny. He actually asked me if it's just a psychological study and the shoes are actually all the same, and this is just to see if he thinks he perceives the shoes as different.
Yeah.
Walter?
I shouldn't ask a question because I didn't hear your talk. But if I put this all together, then it seems to me you change the softness and you changed the heel drop and you related that to comfort. Do you think that softness and heel drop have actually anything to do with comfort? And the reason I'm asking is, when I go into shoe store, and I told that to Nick for the past 40 years, I look for a comfortable shoe. But a comfortable shoe to me means actually that it fits my shoe, my size. I have a very wide and relatively short foot, and so there's certain shoes that I don't even try because I know they are too narrow and too long. And so comfort to me has very little to do with softness or hardness or heel drop or not, but it has a lot to do that I have enough room for my toes and that it fits my foot shape properly.
Yeah, so I agree that fit is a big thing when it comes to comfort. In this study specifically, it was the same shoe, and we only differed changed two properties. So the fit of all 9 shoes should have theoretically been the same, and then we were interested in looking at what comes after the fit. So if the shoe fits well in the store, what do people look out for? Like, do people perceive a hard or soft cushioning as comfortable, or low or high heel drop?
Sabina, were people running fast or like jogging or sprinting? Because I feel like the density of the sole would also affect that. Like, especially if you're like sprinting, like if you look at a sprinting spike, the sole is like very hard plastic because you need that stiffness to propel yourself forward.
Yeah, so the participants in this study, they all ran at the same speed. We controlled that. And it was more like a jog. It wasn't very fast because it was recreational runners, and one of the inclusion criteria was that they run for about 5 kilometers a week. So it wasn't anywhere near professional runners.
Okay.
That's all.
Just a comment. I had a colleague who tested different shoe rotational stiffness, and then he tested several thicknesses, including somewhat painful one, too stiff. And then he asked how participants felt about its insert, and he didn't see any change until some point, and then she stopped after some points when he increased insert stiffness. And then from that point, he said he saw some biomechanical changes in granulation bursts. And then interesting thing was that best performance was in that range.
Okay, do you know where that threshold was as to where they could perceive the difference?
Well, I don't really remember the number.
We can talk after. That's interesting.
Yeah, so maybe you want to include a bit more weight with your
Yeah.
Any more questions for Sabina?
Sure, I have another one.
Oh, let's go to the back and then.
What are your variables with gender? Did you look between the genders to see if there were any differences, and was there any?
There were no differences.
Okay, Sabina, I guess it's a 2-part question. Do you think shoe comfort matters? Like at the end of this, I guess there are 2 options. You either say that shoe comfort really doesn't matter, or you say that there's something wrong with your study design that doesn't allow you to discriminate the effect of shoe comfort. So which camp do you sit in?
I think it depends on the person you're talking about. For some people, they had really strong opinions on the shoes. They said, I would never buy this shoe versus I love this shoe. And others, like 40%, as I said, I think they just don't care. You could probably give them any shoe in the store and they'd be happy with it. So it really depends on the person if comfort's important or not.
So do you think if you had a whole group, 126 people that just composed of these people with really wide about, like really like strong opinions on the shoes, do you think you'd see a difference? Or is like the biomechanics of running was quite robust to differences in external whatever equipment?
I'm not sure. It would probably depend on the differences between the shoes as well. So I doubt that with these samples that you would see anything.
Walter?
If I would do a study where I would like to assess what might relate to comfort, and I had two variables to choose, then one would be the shape of the shoe rather than heel drop softness. So I would measure the people's feet very carefully and then try to find a shoe that fits their foot shape the best, and then would vary the foot shape where I make it a little narrower or a little wider, like in a store where you can buy it. So that would be the first one. I would look for the fit. And the second one would be weight. I would vary the weight. So those would be like two variables.
Yeah, so
And I wonder if you then did that, if you had a heavy shoe, a middle light shoe, and a light shoe, and then one that based on some three-dimensional fit that you do, like digitization of the foot, and then you vary that a little bit narrower, a little bit wider. If you wouldn't find a relationship that would actually relate to comfort.
yeah, so I don't know if I'm allowed to talk about that, but that's actually another study that Adidas has done. They produced a variety of shoes and did some foot scans, and they're just trying to see what kind of foot likes what kind of shoe.
And it didn't work.
We don't have the data. That's
Because those would be two. If I wanted to relate a shoe to comfort, that's not what I would do. That's not what a runner thinks about, I don't think. But then you said you have 5 kilometers per week people, so those are not really runners, yeah.
I've had really opinionated runners that say, I don't run with a shoe that has a greater heel drop than 7 millimeters.
Yeah, but they wouldn't do that, but is that related to comfort?
I think so, yeah. They say they're in pain if they have a greater heel drop.
Sorry to pile in there, I just started thinking about other things. Did experience relate to choosiness? So the amount of volume that the person's running, did that relate to how sensitive they were in?
No.
Nope.
All right, any more questions for Sabina? All right, one last one. Watched this great debate a few months ago about footwear, and the excellent postdocs convinced the audience that no shoes actually might be more comfortable. Should people wear shoes at all? You don't have to answer that. All right, thanks Sabina for a class. So this is our last seminar for the year, and we'll see you back on January 10th, 2019.
For who?
Danielle Whittier.